First of all, go to your notes. Here is PA, not PB. Okay? Correct this point. Second point, if someone wants to recover the laboratory, tomorrow is the last chance that you can have. Okay? So come tomorrow at 8:30. 8:30 and not 9:30 as usually someone does. Okay? Last one. Okay. I want to continue my lectures until Tuesday 10, June 10th. Okay, Tuesday is correct. It's Tuesday. Probably yes. Huh? Okay. So this will be the last lecture. In this way, at the end of this lecture, you will have 78 hours of physics. The number for you is 76. But if I stop on the first Thursday, the previous Thursday, you have only 75, which is less than you merit. And I continue also on Tuesday 10, okay? In this way, you have 78 hours of lectures plus 18 hours of exercises plus 6 hours of lab, which produces a total of 102 hours instead of 100, okay? But, okay, you can tolerate 2 hours more of teaching. Then, next Thursday, which means June 12th, the course is finished. I propose to you a day for your questions, and this day, for me, the best day is on Friday 20. Okay? I will look for a room somewhere, perhaps in my department or I don't know where, okay? And I will be ready all the day for solving exercises, answering questions about the theory and so on, okay? So you have more or less 10 days from the end of the course and this, let me say, consulting time, last consulting time. Then I don't want to meet you until the exam, okay? I don't want to answer your question in the week before the exam. Why, you say? Because very simple, okay? You come and you ask me this theorem, this theorem, this theorem. When you go to the oral, I say, okay, this theorem already explained in the past week, so I don't ask him this theorem. And in this way, if you are very able, you can discard a number of theorems from your preparation because, okay, you already know. So finished, okay? Consulting time on Friday 20, June 20. Is the last consulting time. I will dedicate all the day, morning and afternoon, but you have to prepare yourself before, solve your problem before, because after that day, I don't want to meet you, okay, for obvious reasons, okay? It's clear? I will send an email to everyone to inform you about the time schedule and date, perhaps it changes, and the room, the aulas, okay? Is okay for you? No objection to this? No? Okay. Okay, good. So, let's go on. Going on, we go back to our transformations. And we recall that we have, for a system, we have 3 coordinates, PVT, related by the equation of state. And we know 2 other quantities, which are heat or exchanged heat, exchanged heat, which means the heat coming in or exiting from the system. And we just studied also delta W, which is the work made by the system, okay? Okay? Now, I would like to underline one point. If you are going from one point A to another point B, okay, in general, you change, in each point you change the pressure, volume, temperature in general. Sometimes some of these quantities, these coordinates, are not defined in case of irreversible transformation. And during this transformation, what happens? You can exchange heat. The system can absorb heat or produce, or excuse me, release heat. Okay? Also, changing the volume, the system can produce a work. Okay? In case of reversible transformation, I mean in case of always defined pressure, this work is integral of PDV. Otherwise, is the external work, okay, made by the external forces during the expansion or shrinking of the system. Okay? Of course, the external work is always opposite in sign with respect to the work produced by the system. If the system expands, it means that the pressures, internal pressures, are producing a positive work, but the outside the system decreases the volume, so the work is negative, and opposite in case of shrinking. Okay, but we have delta H and delta W during every transformation. Now let's suppose that you are going from A to B along a reversible transformation, and in this case is let me say well defined at every point of the transformation. Or suppose that you transform your gauge from point A from point to B, I mean from pressure, volume and temperature in A to the pressure, volume and temperature in B, but using another part, I mean using some irreversible transformation, okay? Or also using another reversible transformation, which follows another curve. The question is, the exchanged heat and the produced work are the same if the boundaries of the transformation are the same. I mean, if you go from A to B, the work produced and the heat absorbed or released is the same independently on the path or is depending on the path? The answer is depending on the path, okay? It's not always equal, okay? And we have to demonstrate this fact. In some way, is analogous to what we demonstrated when we demonstrated that the friction, okay, the work made by the friction is not the same if you go from one point xa, ya, za to another point yxb, yb, zb, but depends on the path. You remember that we demonstrated this fact simply calculating two different paths and the work along these two different paths, and we found that they were different. The same we will do in this case, okay? So to demonstrate that there is a difference, we use this example. Let's suppose to have a system which starts from a point A, then moves toward a point B, passing through a C point along an isobaric transformation, and then from C, C is a point having the same volume of the final point B, through an isovolumic transformation. What does it mean, isobaric transformation? Isobaric transformation means same pressure, okay? Same pressure. What does it mean? Isovolumic transformation means same volume during the transformation. You see that in this case, the volume from C to B is always the same, okay? Let's suppose that your system is a gas having n mole, okay? Ideal gas n moles, okay? Which means that PV equal to nRT can be applied and can be applied to all branches of the transformation because from A to C to B we have reversible transformation. Each point is well defined, is in equilibrium. Okay? This is what happens. Okay? Then I want to calculate now I want to calculate work and heat exchanged, work produced and heat exchanged during the transformation ACB, and then I want to look at the work and exchanged heat during the transformation from A to D along a isovolumic and from D to B along the isobaric transformation. Okay? It's clear? Clear this one? Okay? And I want to demonstrate that work and heat exchanged along ACB are different from heat and work exchanged from A in ADB. It's clear? So, well, let me start from the first one, which is A, C, B. Okay? Along this one, okay, we want to calculate the work produced from A to C and then from C to B. Okay? The work will be integral, so delta WACB is equal to integral from A to C of P dV plus integral from C to B of P dV. Okay, the integral is from A to B, but I can split the integral in two parts. Okay, I separated the domain in integration domain in two parts, from A to C and from C to B. This is the usual properties of integral, and you know everything. Immediately, we see that from C to B, which is the variation, infinitesimal variation of volume, is 0. V is constant. dV, the differential of a constant, is 0. So this one is 0. Okay? So we have to write just this integral, to calculate this integral. P along AC, P is a constant. Only the volume is changing. So this becomes P integral from A to C of dV. But this is very simple. Is P, integral of dV is V, which becomes VC minus VA. Of course, VC is equal to VB, so let me change this one into B. Okay? Okay? Do you agree? Okay. So now let me go to A, D, C. Excuse me, A, D, B. A, D, B. Okay? Now delta W of A, D, B is equal to integral from A to B, but again A to D, P dV, plus integral from D to B, P dV. As before, along AD, the volume doesn't change. The differential of the volume is 0. So this integrand is 0, the integral is 0. Equal to, again, from D to B, we have a constant pressure. Constant pressure means that we can take the pressure outside, integral from D to B, okay, from D to B of dV equal to P times integral is V, which means VB minus VD, but again VD is the volume of A, so I can substitute D with A. Are these ones the same? No. Why? Why these two words are not equal? Which is the value of P here along this curve from A to C? Which is the value of P? Is PA. Yes or not? Do you agree? Which is the value of the pressure, okay, from D to B is PD, or also PB is always the same. So here we have PB. So you have the same variation of volume, but the work is made at two different pressures, okay? Surely PA is different from PB, because you see that they are corresponds to different values on the ordinates, okay, value. So the two works are different from this part and this part, okay? It's clear? Second one, we have to check the heat. May I cancel here? Okay, A, C, B. Okay. Along ACB, we want to evaluate the variation of the heat. Okay. So, if the system passes from point A to point C, increasing the volume at constant pressure, okay, which is the heat that that is absorbed or released during this transformation? You have a system, the gas, okay? This gas passes from the point A to point C, from PA, VA to PA, VB, which is the volume, excuse me, which is the heat absorbed. Is a gas, makes this transformation from A to C, okay? Make this transformation from A to C. Making this transformation means changing P, V, and T. But P, V, and T, they are related, okay? P doesn't change. The relationship between P, V, and T is the equation of state of the gas. P is a constant, and changing the volume from A to C, we change also the temperature. Yes or no? If we change the temperature and increasing volume, we increase also the temperature, okay? Means that the system absorbed some heat, okay? Which is this heat absorbed along, let me say, delta H, A, C, which is the heat absorbed. Which will be capacity of the gas times variation of temperature. What is the capacity of a gas? Capacity is mass times specific heat. Do you remember? Okay? Gases in general are measured, the amount of a gas is measured not very often using the mass, but using the number of moles. Okay? In general, you say, I have 2 moles of oxygen. I don't say I have 10 kilograms of oxygen. Okay? So instead of speaking about the specific heat as ratio between heat and mass, we speak about the specific heat as a ratio between the heat and the moles, okay? So the capacity will be defined as number of moles times specific heat of the gas. Let me call Cn. Cn means specific heat with respect to the moles and not with respect to the mass. It's a different way to measure the amount of times variation of temperature, which means Tc minus Ta. Do you agree? Excuse me. C, in case of a gas, we have the problem of the specific heat, which is not always the same in case of transformation of a constant pressure and the transformation of at constant volume. Do you remember what we said at the beginning? So in this case, which kind of a specific heat I have to write? Constant pressure, and indicate this one in this way. Okay? This is what we get. Okay? Then we have also delta HCB, and this one will be equal to N times what? Times from C to B. Which kind of a specific heat I have to use? Cp? Cv, another specific heat at constant volume. So I write here Cv, okay? Times Tc minus Tb, okay? Well, then let me go to the other circuit, and we obtain here for A, D, B, we will have more or less the same. Delta H, A, D is equal to N, C. And which C from A to D? CV, T, D minus T, A, and delta H, D, B equal to N, C, P, in this case, constant pressure, right, of N, times T, B minus T, D. Okay? Now, it's difficult to compare these heats, okay? But we can look at, we can substitute, instead of temperatures, we can substitute the values of pressure and the volume. It's better, okay? Because in this way, we can look at the situation along isovolumic, isopressure, and so on, isobaric. So let me transform this one into N, Cp, N of, instead of T, C, N, we can use N, R. Using this one, we can write P, V in C, and minus P, V in A. Do you agree? Do you agree? Any question about this one? Okay, and the same here, N, C, V, N divided by and R, and instead of TC we use PCVC minus PB, excuse me, is opposite. Final temperature minus initial temperature here. B minus C, excuse me. So this one again, also cancel. P, B, VB minus P, C, VB, VC. Okay? The same must be done below, okay? Equal to N CV N over NR times TD will become P V in D minus P A V A. And below N C P N over NR P PD, PPB, VB minus PDVB. Okay? So now we have to compare all these terms, okay? The heat absorbed during the transformation ACB is the sum of these two ones, okay, which means these two ones. And along ADB is the sum of these two ones, okay? So let me look at the first one. We have N, and you see that N can be cancelled everywhere, cancelled everywhere, cancelled everywhere. And we have CP, PCVC, okay, minus CP, PAVA, plus CV, PB, VB, and PC, VB, VC, PC, VB, VC, okay? Here you have PAVA multiplied by CV and PB, VB multiplied by VC. So let me write all terms. So we have CPN divided by R times PCVC minus P minus CPN over R PAVA. Okay, plus CVN over R PB VB minus CVN over R times PCVC. Okay, this is written so this is equal to delta H ACB. This one is equal to CVN over R PD VD minus CVN over R PA VA plus CP N over R PB VB minus CPN over R times PD PD VD. and this is equal to delta H A D C. Okay, so now we use only the volume and pressure measured in A and B, because C and D are mixed of somewhat like that. So we can say that PC, pressure of C, is equal to the pressure of A. So let me cancel this one and write A. VC is the volume of B. So let me write, instead of VC, VB, VB, correct? PA, the A, and then here PB, VB, and here we have a PC, VC, again, PC, pressure in C is the pressure in A, and the pressure in B, so this is A, and pressure and volume in C is volume of B, correct? Oh, I made a mistake. Okay. PB. No, there is, no, excuse me. PB, VB, PB, VB remains the same. Okay, here PC, VC. Instead of PC, I use PA, and instead of VC, I use VB. Check is correct now. Then as we go to this one, PD, VD, PD is equal to PB, and VD is equal to VA. This remains the same, and here we have PB, VB remains the same, and this one, PD is equal to PB, and VD is equal to VA. Okay? So now, let me look at what is P. So let me change. Okay, excuse me. Is everything is correct up to now? Okay, so we have to every point. So we have CP. So, be silent, please. So one has to make this difference, and you see immediately that this difference is not equal to 0, okay? So, there are a lot of terms. So, PA, VB here. Let me collect in the best way. Yes. Okay, this is the difference of in between them. Shh. Now, this difference is not equal to 0. Why? Often in this case it's not evident to how to transform this one, but one has to go to the temperatures using PAVA, which is proportional to TA, PBVB is proportional to TB, okay? And they are different in between them, so you can collect these two ones, and you find that this one and this one, this one and this one are different because this factor is equal to this factor, but PBVB and PAVA are different. This is equal to, is proportional to the temperature in B, and this is proportional to the temperature in A, okay? These ones also, they are one opposite in sign with respect to this one, and you have a PAVA, you can make the difference in between these two ones, and also in this case you have a number which is not equal to this one. So this sum is different from 0, also for what concerns the heat, okay? So this means that going from A to B along these two paths, okay, we obtain a different exchange of heat of the system with respect to the exchange of heat. So now, how do we write this situation? We say that when we have a transformation, an infinitesimal transformation, okay? We say that we have a variation of dt, a variation of dp, a variation of dv. All these ones produces a variation, an infinitesimal variation of work, dw, and an infinitesimal exchange of heat, delta H. But since these two work and heat are depending on the path, instead of writing dv and dh, we write this symbol, delta W and delta H. Okay? What does it mean? It means that variation depending on path. And the same here. Okay? This symbol, delta W, is an infinitesimal, exactly like the other infinitesimal, but recalls us that this quantity work or this quantity H, they are depending on the path. Okay? So when you go from one point A to another point 8, if you make the integral of the delta W and the integral of delta H, you can do this integral, but you need to specify the path along the plane delta and the plane PV, okay, or all the other ones. It's clear, this point, okay? And this is what happens in general, and looks like the work made by, let me say, dissipative forces, okay? They depend on the path. But now we state the system. Excuse me, we state the first principle of the thermodynamics. The principle is the following. If you make a transformation, infinitesimal transformation, and you change delta t, excuse me, dt, dp, dv, okay, you produce a variation of work, an infinitesimal variation of work delta W, you produce an infinitesimal exchange of heat delta H. These two changes are depending on the path, but their difference is an infinitesimal too. The difference between two infinitesimal quantities is an infinitesimal quantity. But, excuse me, this difference is called U and is a differential which doesn't depend on the path, okay? Variation which doesn't depend on path, okay? Okay, it's clear? So you change you transform a system, a thermodynamical system, from one point to another point very, very close to the first one, okay? Making an infinitesimal transformation, infinitesimal change of all these three coordinates. Okay, you produce two infinitesimal variations of the heat and of the work. This variation, if you you want to integrate the total heat, or you want to integrate the total work, okay, you need to specify which is the path that you are following, but their difference, infinitesimal by infinitesimal, is a quantity which doesn't depend on the path. So if you make the integral of delta H from A to B, you must specify along gamma, and you obtain a result delta H which depends on gamma. The same when you make the integral from A to B of dw, you have to specify the path gamma prime, and this one means that you have a final work which depends on gamma prime. Of course, depend also on AB, okay? Depends also on AB. But when you make the integral of delta H minus delta W from A to B, you obtain a result which is delta U, which depends on A and B, but doesn't depend on any gamma. Okay? This is an experimental observation, which looks like, I don't know, the three laws of the dynamics for one point, okay? And we write this property, this one, in this way. Always. Delta H equal to delta W plus du. This one is the first law of the thermodynamics. And U is called internal energy of the system. Internal energy of the system. Any question on this point? Okay, so remember this form, okay, of the first law of the thermodynamics, okay? The variation of the internal energy is independent on the path that you are doing, while each variation of heat and work, they are depending on the path. Okay, it's quite unusual. Okay, you have two quantities, both are depending on the path, but their difference doesn't depend on the path. Okay, and this difference is called internal energy, defined in this way. Of course, the internal energy of a transformation from A to B will be the integral from A to B of du. Okay, clear? Question? From A to B, same extreme, different paths, same work. Some cases can happen, but special cases, single cases, of course. It's not forbidden, yes, it's not forbidden, of course. Of course. Other questions? No other question. Okay. Well, now... we have time to look at one special case, and the special case is the following. Ideal gas. What happens in the ideal gases? Okay? About an ideal gas, we know that the equation of state is equal to P, V equal nRT. Now, there was made an experiment by Joule, and the experiment was the following. Let's suppose to have a container, a bigger container, and in this big container, in concrete, for instance, very thick, okay, rigid body, absolutely rigid body, let's suppose to make two cavities, connected by a pipe okay, and this pipe was closed by a switch, okay. In one cavity, there was a gas, an ideal gas, n mole of an ideal gas, okay? And there was a thermometer connected here, okay, with the scale, and also a thermometer connected to the other empty cavity, okay? This is the Joule experiment. Okay, so what happens? The gas fills one cavity, the other one is absolutely empty, okay? And at the beginning, the temperature was measured here inside and here inside, okay? And we got, let me say, some temperature T0 in absolute value, okay? Then this switch was switched off, okay? So the situation was this one. And the gas flew from one cavity to the other one very quickly, okay? And got an equilibrium, a new equilibrium, okay? Okay? So, the observation was the following. The temperature didn't change from the initial situation to the other situation, okay? So there was no variation of the temperature after the switching off of the switch, okay? Which is what we can deduce from this experiment, the following. We can write delta H equal to delta W plus du. Okay? For the gas, we observed no variation of the temperature. In principle, U, which depends on the point. At the beginning, we had some point A, and then we had another point with point A, and then we had another point B with higher volume, double or whatever, higher volume. And of course, the temperature was always the same. So this means that if the volume increased, thanks to the nR equal to, nRT equal to PV, okay? If T is a constant, increasing the volume, the pressure decreases. So what happened? We can say U is a function of P, V, and T, correct? In principle. Depends only on the point. You remember from this law, okay, we have that the integral of du depends only on the point, which means that the u depends only on the point, okay? But this concrete was adiabatic, I mean, was an insulator, okay? So no heat passed from the gas to the container or outside, okay? In this way, we had that dH was 0, okay? Then the work, which is the work? Which is the work made by the system against the outside. This transformation is not reversible, of course. It's quite sudden, okay? Which is the work? In case of an irreversible transformation, the work is the work made by the external world against, which is the work made by the concrete against the heat. Concrete is a rigid body. Which is the work. These walls the internal walls of the cavities, which were made against the gas? No one, because they are rigid. They didn't move. Okay, there was no expansion, no shrinking of the walls, internal walls of this concrete. It's clear? So this means that also this one is equal to 0, plus du of PVT. Okay, during this transformation, we had no change of the internal energy. No change of the internal energy. Okay? It's clear? So now, you remember which is the form of a differential of a function depending on several variables. We used this one for error functions and also for potential. This is equal to derivative of u with respect to p times dp plus derivative of u over with respect to v times dv plus derivative of u over dt times dt. Okay? Do you agree? Which is dt in this transformation? 0, temperature remained the same, so this one cancels, okay? But on the other hand, this is equal to 0, okay? And this experiment was repeated, changing the volumes of this container, and also changes the number of moles, okay? So what happens? Happens that changing the volume during this transformation, we have these two quantities which in total they make 0. But we can change dV as we want and dP as we want. Okay? How? Changing the initial temperature. Okay? And we have a different variation of dP and different variation of dV. But their sum must be always equal to 0. And if we are able, we can change dP and change dV, and we obtain always 0 as a sum, means that both coefficients must be equal to 0. In other words, du in dP and du in dV must be equal to 0 in order to have 0 on this side. Okay? But what does it mean, du in dP depending on 0? Means that u, in principle, is equal to 0. If the derivative with respect to p is equal to 0, means that u doesn't depend on p, correct? So I cancel p here. But also is du in dv equal to 0. This means that also the volume is not affecting anything in the variation of the internal energy. So again, internal energy doesn't depend on v. So means that the internal energy of an ideal gas is only depending on T. Okay? Okay, so this is a very important conclusion. Okay? For an ideal gas, the internal energy is a function only of the temperature and not of the pressure, not of the volume. Okay? So if you have n mole of gas, these n moles, they contain an amount of internal energy which depends on the temperature. Okay? And this is the final conclusion about the ideal gases. Next lecture we will look at various variations, various transformations of the ideal gases. See you on Thursday.